Hey, hello. Assalamu alaikum, guys. How are you? So we'll meet again in a lecture for instrumentation. Today we're going to talk about Wheatstone bridge. Okay. Um, okay, guys. You can check with your slides. You can refer to lecture 7. Now we are looking at Wheatstone bridge. So basically, just to recap again, for the whole syllabus, we have divided the thing into 3 sections. The first section is on the more of introduction, the theory of instrumentation, seeing how the characteristic of the sensors. We have seen operational characteristic, we have seen static, and we have seen dynamics. After that, we are looking at how, when we have a lot of information, how to handle the data. We look at how statistically we can calculate the error and all that. So from there, we are looking at, if I can recall, the transfer function, looking at how information is changing from input to output of any sensors or transducers because of the transfer function. We have seen also sensors that work using the first order system and also the second order system. And from there, when we finish the first part, we are looking at the second part, which is the signal conditioning. And in the signal conditioning, we are looking at op-amps, operational amplifiers. And from there, we see how this op-amp can be used to build up many kind of system. For example, you have the voltage follower system, we have differentiator, we have integrator, we have comparator, we have summation circuit, and many others. And now, the last chapter on section 2 is Wheatstone bridge, basically. All right. When we finish Wheatstone bridge, we are going to continue into sensors and transducers part, in which we're going to see a lot of other sensors, basic constructions, the model, the formulation, the basic, so that from there you can see how information or environmental or physical parameters are sensors through these sensors basically. Right. So moving around the bridge circuit, actually, the bridge circuit is very much needed to convert the information from the sensors and connecting to the other signal conditioning circuits. All right. So bridge circuit is basically an interface between the sensors and some other circuit after the in the signal conditioning systems. All right. So in most of the cases, we have our sensors working to produce changes in terms of impedance or in terms of resistance. So by a sensor, you put a sensor into some, environmental settings. You want to measure some parameters, for example, temperature, humidity, speed, pressure, many others. All you are getting from the sensors is changes of R. So the R is, for example, changes from 10 ohms to 20 ohms, and you are observing many sensors are basically produce this kind of values, parameters, in R, changes of R. So have sensors changing impedance to detect, to denote the changes in the environmental parameters that they are measuring, basically. So when we have this R coming out from the sensors, what do we do with the value, in order to get to read this thing correctly to our systems? So the most common and the most popular type of I would say interfacing circuits for this kind of sensors is Wheatstone bridge. You can simply call it bridge circuits. All right. So bridge circuit is primarily used to convert impedance, from the input sensors and pass it back to the whatever circuits after the bridge circuit that you can put on. All right. So they have the advantages here. Voltage produced varies around 0 So basically, this kind of circuits actually is very sensitive to any input signal and can produce a wide variety range of output signal. Basically, you can tune these bridge circuits towards the range of your working input impedance level, so that it produces some kind of voltage at the output stage, in which also you can basically control this output voltage range by putting a different configuration of the circuits, basically. All right. So this is the diagram of a very basic design of Wheatstone bridge. As you can see, um, you have E as a voltage supply over there, and then going through you are looking at the point A, where when you go down you have two resistors, and then after that you have another two resistors that connect to the point B. In between you have point C and point D, and right in the middle you have G over there. Okay, so again, E is your supply system voltage, so you can take any voltage that fit to your system. Okay, then point number one, you can see that the circuit consists of 4 resistors in diamond orientation with resistive transducers in one or more legs. So you can see point C to B, you have one resistor. You have point D to point B, you have one resistor. So both of the resistors are called leg resistors, which the sensors are connected. Okay, so if you have a sensor, okay, so you want to connect the sensor to the Wheatstone bridge, you have to connect to R3 or RX, meaning that you have to remove R3, replace R3 with your transducer, your sensors, okay, or you can remove RX over there, okay, and you can replace the RX with your transducer, okay. So you have, again, looking into the networks of resistance, you have R1, R2, R3, and R4. Please take note on the orientation. Please take note on the position of R1, R2, R3, R4, because this position is going to define the formula that we are going to see later on. Okay. Again, in the circuit, look at point C and point D. This is the output of the circuit. Okay. As I mentioned before on the previous slides, this circuit is meant to convert variation of R resistance in the input, in which you have to connect the sensors to R3 or RX, and then the circuit is going to produce output voltage in proportion to the input change in the R. Okay. So the output voltage here is measured in G, where the voltage points at point C and point D, we are measuring some potential across these 2 points, okay, point C and point D. Okay. So this is same diagram just now in a large version. You can see now R1 is changing position with R2, and R3 is R4 is the same. Basically, you can follow the standard convention of the, aiming the R into the position. You can basically create your own, but you have to be sure that because after this we are going to develop some formulation from this very diagram, and the index of 1, 2, 3, 4 here actually plays some role. So if you change the position, you have to change the index in the formulation later on. Okay, but this is the, what they call that, naming convention and the index orientation that are pretty much standards. R1 is on the right, upper right, R2 is the upper left, R3 is basically down there to the left, and Rx or R4 is basically down to the right. Okay, this is the very common orientation. I hope you can stick to this. Okay, so D, basically from this diagram, you can see D is basically voltage potential between point A and point B. It's also referring to the same thing as G here. galvanostat here is more or less measuring potential between point C and point D. So G and D is the same thing. Okay. So now we are looking at the potential difference between point A and point B denoted by delta V. So VA is potential at the point with respect to C, and VB is potential to point D with respect to C. Let me look at again. Here you have VA and VB. Now we are looking at VA's potential at point A with respect to C, and V at point B, we are looking at the voltage potential of at B with respect to C. Okay? So, for example, here voltage at A, the formula, VA is VR3 over R1 plus R3. So VA is basically taking the one of the leg resistor R3. We are measuring the potential that drop at resistor R3 at point A. Okay. So we are taking voltage divider formulation concept at point A, which is V is the system supply multiplied by R3, and then divide by R1 plus R3. Okay, that's voltage at point A of VA. Now, if we shift to VB, voltage potential at point B, basically you are looking at the voltage drop at R4. Okay, so this is how the formula goes: is V multiplied by R4 over R4 plus R2. Okay, so this is just a concept, voltage divider concept, and you have VB now, and of course V is the system supply. Then you put it together, you have VA minus VE, which is the delta V. So you will have delta V is equal to VR3 over R1 plus R3 minus VR4 over R2 plus R4. So you can put this thing together, you get the formula below. Okay. So you have to more or less understand where this formula is coming from and how to derive them. And of course, it's good if you can memorize them too. Okay. Okay. There are situations where the AV, delta V, or the voltage difference, the potential difference are 0. Okay. Not necessarily voltage at point A or point B is 0. Voltage at point A or point B can take some values, but in this case, the voltage potential difference is 0, meaning that if you take VA minus VB, is going to be 0. Okay. VA can be 4 volts, VB can be 4 volts. Okay, but if you minus them, they are 0. No, this is a null bridge, or voltage potential is 0. Okay. Some of the students think that at this point VB is 0 or VA is 0. Can take those two values, but not necessarily they have to be 0. They can be more than 0. It can be 1, it can be 2, it can be 3, it can be 4 volts. But here the point is VA and VB is the same, taking the same value. Then VA is 3 volt, VB is 3 volt. So if the value are more or less the same, the potential difference are going to be 0. This is where you call a null bridge or balance bridge. To achieve this, there are some conditions. Look at the formula: R3 multiplied by R2 is equal to R1 multiplied by R4. So if we look at the bridge here, okay, you have R1 multiplied by R3, okay, equal to R2 multiplied by R4 or Rx here. Okay, so that's if these two values are equal, then you have a null bridge. And null bridge, basically you can take these two formula and it works basically. Okay. So let's take one example so that you know basically how and when to use the formula. The question says, so if a Wheatstone bridge null, which R equal to 1000 ohm, R1 is 1000 ohm, R2 is 142 ohm, and R3 is 500, find the value R4. So you have the keyword here, bridge null, meaning that you can use the formula of R3 multiplied by R2 equal to R1 multiplied by R4. So you can, take out the formula, fill up the, substitute the what they call that resistance value with the given one. So you will finally have R4 is equal to 431 ohm basically. Okay. So the second example here also talk about the same thing. You can use back the formula. There are values given. You can use back the formula. You just fill up the thing, substitute the value, and you will get delta V equal to those values. Very simple calculations. All right. So we are talking about null bridge. The bridge is more or less balanced. VA and VB is the same. You can take any value. It can be 0, it can be 4 volts, it can be 2 volt, it can be 1.5 volt, it can be 0 volt. Okay. VA and VB the same. Is potentially, the difference potential is 0. Basically, it's a null bridge, it's a balanced bridge. V out is equal to 0. Okay. For this particular setup, the V out is equal to 0. Suddenly, in this case, we have some very small changes in one of the leg resistors, R3. Okay, so now R3 is experiencing some small change. It's becoming delta R3. Okay, so when R3 is changing, basically the null bridge condition is no longer is no longer whole. So you have a not null situation in which you will have the output voltage is no longer 0. There will be some changes in the output voltage. All right. So this is what the bridge is designed for, to detect the very small changes in one of the leg resistors. Okay, so if you look at the equation delta V, which we derived previously, you have to replace here the R3 with delta R3. Then you can simplify the whole thing. You will get finally delta V is equal to delta R3 over R over 4 plus 2 in the bracket of delta 3 plus R basically. This condition, if R1 is equal to R3 is equal to R4, they are all R. So you can replace R1, R2, R4 equal to R, and this is more or less what you get when you have changes in one of the resistors. Okay, so Wheatstone bridge application doesn't only work with sensors that produce R changes. You can also arrange some of the sensors that produce different kind of output, for example, capacitive or inductive. You can basically arrange them in the same diamond orientation as the Wheatstone bridge circuit. And looking at this diagram, you have Z3 and Z4 here. You can put capacitors at Z3 and Z4, Z1 and Z2, and you can also put inductors in this position. We have seen so far resistors are being put there as R1, R3, R2, R3, R4. You can also replace C1, C2, C3, C4 for the capacitors, and it still works the same because all of the sensors basically produce difference in terms of impedance. They produce variation, and you have changes in the parameters that you are measuring. The sensor will put out some kind of changes or variation in terms of impedance. Okay, which you can always measure and put the sensors in the configuration of Wheatstone bridge, and you can potentially detect the voltage output D here in this diagram, which corresponds directly to the input Z3 or Z4. Okay, so I think that's all for the lecture in the topic of Wheatstone bridge. Okay, I'll see you again in the next topic.